Hello, everyone, and a huge welcome to this coding adventure. Have you ever looked at incredible AI models like Llama or ChatGPT and thought, that's amazing, but how does it actually work? It can feel like magic, but today we're going to pull back the curtain and become the magicians ourselves. The full code is available on our GitHub. Check the link in the video description. In this video, we're not just going to talk about large language models. We are going to build one from the ground up using PyTorch. We'll write every line of code, understand every component, and by the end, you'll have a working mini-LLM that you trained yourself. This is a hands-on journey from a blank script to a text-generating AI. So, grab your favorite drink, open up your code editor, and let's get started. Before we start coding, let's look at our roadmap. Building a language model is a journey with several key stops, and we'll be visiting every single one. First, we need to create our tokenizer. Think of this as teaching our computer a new language by creating a dictionary. It needs to know how to break down human text into numerical pieces it can work with. Next up is data preparation. Once we have our dictionary, we need to read our book, our text dataset, and convert the whole thing into a format the model can train on. We'll also create a system to feed it data in small, manageable batches. Then comes the main event, building the model itself. This is where we'll construct the transformer architecture, the brain of our operation, layer by layer. After that, we'll set up our configuration file. This is like the settings menu for our project, where we can easily tweak all the important numbers. With everything in place, we'll write our training script. This is where the learning happens. We'll feed the model data and watch it get smarter over time. And finally, the moment we'll all be waiting for, inference. We'll load our trained model and start a conversation with it, prompting it to generate new and original text. It's a complete journey, so let's take our first step. Alright, first stop, Tokenizer.py. Our model can't read words like hello or world, it only understands numbers. The Tokenizer is the translator that bridges this gap. We're using a library called SentencePiece to train what's known as a byte pair encoding, or BPE, tokenizer. This is a really clever approach. Instead of just splitting by words or characters, it learns the most common subwords from our text. So it might learn that ing, the, and trans are very common and should be their own tokens. We call the train function and give it our text file. I'm using a Wikipedia dump here. We tell it the model type is BPE and set our desired vocab size, which is how many words we want in our dictionary. The most important argument here is byte fallback equals true. This is our safety net. It means if we ever encounter a weird symbol or a character from another language, our tokenizer won't crash. It will just fall back to representing it by its raw bytes. This makes our tokenizer incredibly robust. When we run this, we get two files, a .model file, which is the trained tokenizer logic, and a .vocab file, which is the dictionary it created. After training our tokenizer, it's always a good idea to make sure it works as expected. That's what these next two functions are for. Think of it as a quick sanity check. The load tokenizer function is our way of loading the trained .model file back into our program so we can use it. It creates a sentence piece processor object which has the encode and decode methods we need. The test tokenizer function puts it to the test. First, it takes a sample sentence and calls tokenizer.encode. This converts our human-readable string into a list of integers, according to the vocabulary we just trained. Then, it immediately calls tokenizer.decode on that list of integers. This should hopefully give us back our original sentence. Running this script and seeing the original and decoded text match perfectly gives us the confidence that our tokenizer is ready for action. Okay, our tokenizer is ready. Now we need to prepare our mountain of text data for training in datautils.py. First, look at the load or create data function. Tokenizing a large text file can take a little while, and we don't want to do it every single time we run our training script. So this function is a smart utility. The first time you run it, it reads your text file, encodes the entire thing into a long sequence of tokens, and saves it to a file called encoded data point t. Every subsequent time you run it, it will see that the file already exists and just load it directly, saving you a ton of time. Next, get, train, valid data does a simple but crucial 90-10 split. We'll use 90% of our data for training the model and hold back the remaining 10% for validation, which helps us check for overfitting. Finally, getBatch is our workhorse. At every step of training, the model needs a small chunk of data. This function goes into our dataset, randomly picks a few starting points, and slices out sequences of a fixed context length. It then creates X, the input, and Y, the target. Remember, Y is just X shifted one token over. The model's job is to look at a sequence of tokens in X and try to predict the corresponding token in Y at every single step. Now for the part you've been waiting for, model.py. We're starting with the absolute heart of the transformer, the head of self-attention. This is where the magic happens. Imagine a token is a person in a crowded room trying to understand a conversation. To do that, it needs to pay attention to other people. In our model, each token creates 3 vectors to help it do this: a query, a key, and a value. The query is like the token asking, "I'm a verb. Who around here is a noun that I might be related to?" The key is like every other token holding up a sign saying, "I'm a noun" or "I'm an adjective." The value is the actual meaningful content that each token holds. In the forward method, we first calculate the attention scores. We do this by taking the dot product of every token's query with every other token's key. This tells us how much each token should pay attention to every other token. But here's a crucial rule. In language, you can't know the future. A token at position 5 shouldn't get information from a token at position 6. That's where our trill mask comes in. We mask the attention scores to hide all future positions, ensuring information only flows from the past to the present. Finally, after a soft max to normalize the scores, we use these attention weights to create a weighted sum of all the value vectors. The result is a new, improved vector for each token that is now enriched with context from all the other tokens it paid attention to. So, a single self-attention head is great, but it's like having just one person trying to understand all the different relationships in a text. What if one head is good at finding subject-verb relationships, but another is better at linking pronouns to nouns? That's the idea behind multi-head attention. It's like having a team of specialists. The multi-head class simply creates a list of our head modules and runs them all in parallel on the same input. In the forward method, you can see we get a list of outputs, one from each head. Each head has focused on something different. We then torch.cat them together, effectively lining up all the specialist reports side by side. This concatenated result is now very rich, but it's also very wide. So we use a final combine linear layer to project it back down to our model's standard embedding size. We've successfully gathered information from multiple perspectives and fused it into a single powerful representation. After our tokens have gathered all this great context from their neighbors through multi-head attention, they need some time to process it. That's the job of the forward layer. You can think of attention as the communication step and the feed-forward layer as the thinking step. This part of the network processes each token individually. If you look at the structure, it's a very standard 2-layer neural network. We take the output from our attention layer, project it to a much larger dimension, in this case 6 times larger, apply a GELU activation, and then project it back down. This expansion and contraction pattern gives the model more capacity to find complex patterns and nonlinear relationships within the features of each token. It's a simple but vital part of the transformer's power. Okay, team, Let's assemble our Lego bricks. We've built the attention piece and the feed-forward piece. Now we'll put them together into a single, repeatable block. This transformer block is the fundamental unit that we will stack to create the depth in our network. The structure is very elegant and follows a consistent pattern. The input X comes in, and first it passes through a layer norm. Then it goes into our multi-head attention layer. The output of that is then added back to the original input X. This X plus is the famous residual or skip connection. It's incredibly important because it allows gradients to flow directly through the network during training, which makes it possible to train very deep models without them forgetting the original signal. After that first sublayer, the pattern repeats. The result goes into another layer norm, then into our forward layer, and finally through one more residual connection. This add and norm pattern is a cornerstone of modern deep learning architectures. Now for the grand assembly. In the GPT class, we take our block and stack it up to create the full model. Let's look at the init method. We start with two crucial embedding layers. The token embeddings layer converts our input token numbers into dense vectors, but the model also needs to know the order of the tokens. That's where positions embedding comes in. It provides a unique vector for each position in the sequence. Without this, our model would just see a jumbled bag of words. Then, we create our blocks by making a nn.sequential container with n layers copies of our block class. This is the deep part of our network. After the blocks, a final layer norm and a final linear layer project the output back to the size of our vocabulary, giving us a score for every possible next token. Finally, notice the init weights method. We're not just using the default random weights. We're applying a specific initialization scheme that is known to work well for training transformers, which helps our model converge more smoothly during training. Let's break down the two most important methods in our GPT class. First, the forward method. This is what happens during a single step of training. We take the input token IDs, look up their token embeddings and their position embeddings, and simply add them together. This combined vector, which now contains information about both what the tokens are and where they are, is then passed through our entire stack of transformer blocks. The final output, the logits, is a giant tensor of scores. If we're training, we're also given the targets. Our goal is to calculate how far off our predicted scores were from the actual correct next tokens. We do this using cross-entropy, which gives us a single number, the loss. The whole goal of training is to make this number as small as possible. Second is the generate method, which is the fun part. This is how we generate text. It works in a loop. In each iteration, it takes the text generated so far, passes it through the model to get the logits for the very next token, converts those scores into probabilities using softmax, and then samples a new token from that probability distribution. It then appends this new token to our sequence and repeats the process. This predict, append, repeat cycle is what allows the model to write text one token at a time. Let's take a quick look at config.py. This might seem like a simple file, but it's one of the most important for doing serious research and experimentation. Think of this as the main settings menu or control panel for our entire project. Every important number that defines our model or our training process is here. We have the architecture parameters like batch size, the context window, the embed size, and how many n layers and n heads to use. We also have our training hyperparameters like the learning rate. If you want to see what happens when you train a deeper model, you just come here and change n layers from 7 to 12. If you want to try a different learning rate, you change one line. This practice keeps our main code clean and makes running experiments incredibly easy and organized. Alright, it's time to put on our trainer hats and step into train.py. The main function here orchestrates our entire training run. It starts by loading our tokenizer and data. Then it instantiates our GPT model. Now, here's a neat professional trick in the optimizer setup. We're using Atom W, a fantastic modern optimizer. But we're not applying weight decay, a type of regularization, to all parameters equally. It's often found that applying it to biases or layer normalization parameters can be less effective or even harmful. So we split our parameters into two groups. The first group gets the parameters with two or more dimensions, like the weights in our linear layers, and we apply our full weight decay to them. The second group gets the one-dimensional parameters, like biases, and we turn weight decay off for them. We also set up a cosine annealing LR scheduler. This will start with our initial learning rate and smoothly decrease it in a cosine curve over the course of training, which often helps the model settle into a better final minimum. Training a large model can take hours or even days. Imagine you're 10 hours into a 12-hour training run and your power goes out. It would be a disaster if you had to start over. That's why checkpoints are our saviors. This block of code checks if a checkpoint file already exists. If it does, it loads not just the model's weights, but also the state of the optimizer, the last iteration number, and the best validation loss achieved so far. This allows us to seamlessly resume training right where we left off. Next is the calculate loss helper function. This is how we'll periodically check in on our model's performance. Notice the first and last lines inside the function, model.eval and model.train. This is crucial. Model.eval tells PyTorch to turn off any layers that behave differently during training and testing, like dropout. This gives us a stable, deterministic loss value. After we're done evaluating, we always remember to switch back to model. Train mode to turn those layers back on for the next training step. All right, here we are at the engine room of our project, the main training loop. This is where the learning actually happens, step by step, for hundreds of thousands of iterations. At every single step, we do 4 things. First, we get batch to grab a fresh chunk of training data. Second, we do the forward pass. We feed the batch to the model and get back our loss. Third, we do the backward pass, which is where the learning occurs. We call optimizer.zeroGrad to clear out any old gradients. Then, loss.backward calculates the gradients for this specific batch. It figures out how to adjust each weight to reduce the loss. We then clip grad norm to prevent our gradients from becoming too large and unstable. Finally, optimizer.step actually applies the updates to the model's weights. Fourth, every so often, as determined by eval interval, we pause to evaluate the model. We print the validation loss, and if it's the best score we've seen so far, we save a new checkpoint. This loop is the rhythm of deep learning: forward, backward, update, evaluate, and repeat. After all that hard work training, it's time for the grand finale in Inference.py. This script is all about interacting with our trained model. The setup is simple. We load our tokenizer and our best saved checkpoint file into our GPT model structure. The most important line here is model.eval. This officially puts the model into inference mode, turning off dropout and other training-only features. Then we enter a simple while loop that lets us talk to our AI. We get a prompt from the user's input. We use our tokenizer to encode that text into a tensor of token IDs. Then we pass these IDs to our model's generate method, which, as we know, autoregressively predicts new tokens. Finally, we take the list of generated token IDs and use our tokenizer's decode method to turn them back into a human-readable string, and we print it to the screen. This is where we get to see the creativity and knowledge our model has learned from the data. So let's take a moment to appreciate what we've just accomplished. We have built an entire end-to-end language model pipeline from absolute scratch. We created our own tokenizer. We built a data pipeline. We implemented a transformer from its most basic components. We wrote a robust training script with checkpointing and evaluation, and we created an inference script to use our model. You haven't just used an API, you've built the engine behind it. You now have a deep, practical understanding of the technology that is changing the world. I encourage you to take this code, experiment with it, change the configs, train it on your own data, and continue your learning journey. Thank you so much for building this with me today. If you enjoyed this deep dive, please give the video a like, subscribe for more tutorials like this, and let me know in the comments what you're inspired to build next. Happy coding!